For as long as humans have gazed up at the night sky, one question has remained at the heart of our curiosity. Are we alone in the universe? The search for another Earth is not just about finding planets that resemble our own. It is about answering one of the most profound mysteries of existence. If life exists elsewhere, it would reshape our understanding of the cosmos, our place in it, and perhaps even the future of humanity itself. The desire to find another world like Earth is deeply rooted in both science and imagination. Throughout history, ancient civilizations speculated about other worlds beyond our own. Philosophers in ancient Greece pondered whether countless unseen Earths might exist in the heavens, each with its own inhabitants. In some mythologies, celestial bodies were believed to be homes to gods or spirits. Even before the first telescopes, the idea that other planets could support life was already embedded in human thought. However, it wasn't until the advancement of modern astronomy that the search for such worlds became a scientific pursuit. Before the discovery of exoplanets, planets that orbit stars beyond our sun, many believed our solar system was unique, possibly even the only one of its kind. This idea was shattered in the late 20th century, when astronomers confirmed the existence of planets orbiting distant stars. In the decades that followed, the number of known exoplanets grew into the thousands, revealing an astonishing variety of worlds, some eerily similar to Earth, others vastly different from anything we had imagined. This explosion of discoveries changed our understanding of planetary systems and forced scientists to reconsider the conditions necessary for life. Planets far larger than Jupiter were found orbiting extremely close to their stars, defying expectations of planetary formation. Some planets orbit not one, but two or even three stars, creating a cosmic dance of light and shadow across their skies. Others are covered in endless oceans, locked in eternal darkness, or blasted by radiation that would make life as we know it impossible. Despite this diversity, astronomers remain focused on a particular goal: finding another Earth. But what does that really mean? In simple terms, an Earth-like planet would need to be rocky, similar in size to our own, and orbit within the habitable zone of its star, the region where temperatures allow for liquid water to exist on the surface. Yet habitability is more than just the right distance from a star. Earth itself has many factors that allow it to sustain life, from its protective atmosphere to its magnetic field that shields it from harmful radiation. A true Earth twin would need to have a stable climate, a balance of chemical elements, and possibly even geological activity to recycle essential nutrients. Scientists use several methods to detect and analyze exoplanets, each with its own challenges. The transit method, which detects tiny dips in a star's brightness when a planet passes in front of it, has been the most successful in finding distant worlds. However, this method relies on a precise alignment between the planet and its star, meaning countless potentially habitable planets may remain undetected. The radial velocity method, which measures the slight wobble of a star caused by the gravitational pull of an orbiting planet, has also proven effective, but it works best for massive planets that exert a strong influence on their stars. Other techniques, such as direct imaging and gravitational microlensing, offer additional ways to find exoplanets, yet they come with their own difficulties, particularly when it comes to detecting small, Earth-sized planets at vast distances. Even when a promising exoplanet is discovered, confirming its habitability remains a major challenge. Most exoplanets are so distant that telescopes can only gather limited data, such as their size, mass, and distance from their star. Determining whether they have atmospheres, liquid water, or even conditions suitable for life requires more advanced technology than what is currently available. The next generation of space telescopes, such as the James Webb Space Telescope and upcoming observatories, will play a crucial role in analyzing the atmospheres of distant planets. By studying the light that passes through these atmospheres, scientists hope to identify chemical signatures such as oxygen and methane, possible indicators of biological activity. However, finding another Earth is not just a technological challenge. It is also a question of probability. Earth has undergone a precise sequence of events that led to the emergence of complex life. Its distance from the Sun, its large moon that stabilizes its rotation, its protective magnetic field, and its geological activity have all played roles in creating a life-supporting environment. If any of these factors had been different, Earth might not have developed the conditions necessary for life to thrive. The same complexity applies to exoplanets. Even if a planet exists within the habitable zone, other factors such as strong radiation from its star, an unstable orbit, or an atmosphere dominated by toxic gases could make it uninhabitable. The search for another Earth is more than a scientific endeavor. It is a reflection of our desire to understand the universe and our place within it. If we do find another Earth, it would be one of the most significant discoveries in human history. It would confirm that our planet is not unique, and that life may be a common feature of the cosmos. On the other hand, if after decades of searching we find no true Earth twins, it would suggest that our world is a rare exception, a fragile oasis in an otherwise barren universe. As our instruments improve and our knowledge expands, we may one day answer the question that has fascinated humanity for centuries. Whether we find an Earth-like world teeming with life or a universe filled with silent, lifeless planets, each discovery brings us closer to understanding the nature of existence itself. Now that we understand why the search for another Earth is so important, let's explore what makes a planet truly habitable. For a planet to be considered habitable, it must possess a delicate balance of conditions that allow life to emerge and thrive. While Earth serves as our only known example of a life-bearing planet, the discovery of thousands of exoplanets has expanded our understanding of what it means for a world to be potentially habitable. The search for another Earth is centered around identifying planets with similar conditions. Yet as we explore further, we must also consider the possibility that life may exist in forms and environments beyond our expectations. One of the most well-known criteria for habitability is the presence of liquid water. Every living organism on Earth, from the simplest bacteria to the most complex animals, depends on water to survive. Because of this, astronomers focus on finding planets located in what is known as the Goldilocks zone, a region around a star where temperatures are just right for liquid water to exist on the surface. If a planet is too close to its star, it may be too hot, causing any water to evaporate into space. If it is too far, water would freeze into ice, preventing the chemical reactions necessary for life. However, the presence of liquid water alone is not enough. A planet's atmosphere plays a crucial role in maintaining a stable climate. Earth's atmosphere not only provides the air we breathe, but it also regulates temperature, traps heat, and protects us from harmful radiation. Without an atmosphere, a planet might have extreme temperature swings between day and night, making it difficult for life to survive. Venus, for example, is similar in size to Earth and is located just outside the inner edge of the Sun's habitable zone. However, its thick atmosphere is filled with carbon dioxide, creating a runaway greenhouse effect that raises surface temperatures to over 400 degrees Celsius, making it inhospitable to life as we know it. In addition to an atmosphere, a planet's magnetic field is another key factor for habitability. Earth's magnetic field acts as a shield, protecting the surface from high-energy radiation and charged particles from the Sun. Without this protection, a planet's atmosphere could be gradually stripped away, as is believed to have happened on Mars. Despite evidence that liquid water once flowed on its surface, Mars lost much of its atmosphere over time, leaving it cold, dry, and exposed to intense radiation. If a planet lacks a strong magnetic field, it may struggle to retain the conditions necessary for sustaining life over long periods. Another important factor is planetary size and gravity. A planet that is too small may not have enough gravitational pull to hold onto an atmosphere, leading to rapid atmospheric loss. On the other hand, a planet that is too massive could have an atmosphere that is too thick, creating extreme pressures that might be unsuitable for life. Super-Earths, planets larger than Earth but smaller than Neptune, are of particular interest because some may have the right balance of gravity and atmospheric conditions to support life. However, their increased gravity could also make it difficult for life to develop in ways similar to what we see on Earth. Geological activity is another crucial factor in planetary habitability. Earth's active geology helps regulate its climate by cycling carbon between the atmosphere and the planet's interior. Volcanic activity releases gases that contribute to atmospheric composition, while plate tectonics help recycle essential minerals and maintain a stable surface environment. A planet without geological activity might struggle to maintain a stable climate over billions of years, reducing its potential for hosting life. While Earth's conditions seem ideal for life, scientists also consider the possibility that alternative forms of life could exist in extreme environments. On Earth, we have discovered organisms called extremophiles that thrive in places once thought to be uninhabitable, such as deep-sea hydrothermal vents, acidic lakes, and even radioactive waste sites. These discoveries suggest that life may be more adaptable than previously believed. If life can survive in such harsh conditions on Earth, it raises the question, could life also exist on exoplanets with extreme climates? Some scientists propose that certain exoplanets outside the traditional habitable zone may still support life. For example, icy moons such as Europa and Enceladus, which orbit Jupiter and Saturn, are covered in thick layers of ice, but are believed to have vast subsurface oceans heated by gravitational forces. If similar conditions exist on exoplanets, life might not need a warm surface to survive. It could instead thrive beneath icy crusts or within underground reservoirs. Another question that remains unanswered is whether life always originates on the planets where it is found, or if it can travel between worlds. The concept of panspermia suggests that life, or at least the building blocks of life, could be transferred from one planet to another through space debris. If a meteorite from a habitable planet were ejected into space by an impact event, it could theoretically carry microscopic life forms to another world, seeding life elsewhere. If this theory holds true, then life may not only exist in multiple places, but could be connected across different planets. As we continue our search for another Earth, scientists must consider all of these factors when evaluating a planet's habitability. While the presence of liquid water, an atmosphere, and a stable climate are the primary indicators, we must also remain open to the possibility that life may exist in environments we have yet to fully understand. Now that we've defined the key ingredients for habitability, let's look at the most promising planets that fit this description. The search for another Earth has led scientists to discover thousands of exoplanets, each with its own unique characteristics. While many of these worlds are gas giants or barren rocky planets, a select few stand out as potentially habitable. These planets share key similarities with Earth, such as their size, distance from their star, and atmospheric composition, making them some of the most exciting discoveries in modern astronomy. Some of these planets orbit faint red dwarf stars, while others circle stars more similar to our Sun. The question remains, could one of these worlds be the home to extraterrestrial life? One of the most important missions in exoplanet discovery was the Kepler Space Telescope, launched by NASA in 2009. Over nearly a decade, Kepler revolutionized our understanding of exoplanets, detecting thousands of new worlds by observing the tiny dips in starlight caused by planets passing in front of their stars. Among its many discoveries, Kepler identified several Earth-like planets in their star's habitable zone, places where liquid water could exist on the surface. These planets remain some of the strongest candidates for habitability. Kepler 452b, often called Earth's cousin, was one of the most promising exoplanets discovered by Kepler. Located approximately 1,400 light-years away, this planet orbits a Sun-like star and has a diameter about 1.5 times that of Earth. Its location in the habitable zone means it could have conditions suitable for liquid water, and it has likely maintained a stable climate for billions of years. However, scientists are still unsure about its atmosphere and whether it is rocky like Earth or covered in thick clouds similar to Venus. Another exciting discovery from Kepler was Kepler 186f. This exoplanet, located 500 light-years away, was one of the first Earth-sized planets found in a star's habitable zone. Unlike Kepler 452b, this planet orbits a red dwarf star, which is smaller and cooler than the Sun. While this means the planet receives less energy, red dwarf stars are known for their violent solar flares, which could make conditions on the planet less hospitable for life. However, if Kepler 186f has a strong atmosphere and a protective magnetic field, it could still be a suitable place for life to exist. One of the most intriguing planetary systems discovered so far is TRAPPIST-1, located just under 40 light-years away. This system is home to 7 Earth-sized planets orbiting a small, cool red dwarf star. Out of these 7 planets, at least 3 are in the habitable zone, making TRAPPIST-1 one of the most promising locations for finding extraterrestrial life. These planets are tidally locked, meaning one side always faces the star, while the other remains in perpetual darkness. This could create extreme climate conditions, but if the planets have thick enough atmospheres, they might be able to distribute heat more evenly and support life. The TRAPPIST-1 system has fascinated scientists because it provides multiple opportunities for studying potentially habitable worlds. With 3 planets in the habitable zone, astronomers can compare their conditions to see how factors like atmosphere and radiation affect habitability. Future telescopes, like the James Webb Space Telescope, are already beginning to analyze these planets in greater detail, searching for atmospheric gases like oxygen and methane that could indicate biological activity. Another significant discovery is Proxima Centauri b, the closest known Earth-like exoplanet. Located just over 4 light-years away, Proxima Centauri orbits the red dwarf star Proxima Centauri, which is the closest star to our Sun. The planet is roughly the same size as Earth and orbits within its star's habitable zone, making it one of the most exciting targets for future exploration. However, Proxima Centauri is known for its intense solar flares, which could strip away the planet's atmosphere over time. Scientists are currently studying whether Proxima Centauri b has an atmosphere capable of shielding it from these harsh conditions. Beyond these well-known exoplanets, other promising candidates continue to emerge. One such world is LHS 1140b, a super-Earth located 48 light-years away. This planet is about 1.5 times the size of Earth and orbits within its star's habitable zone. Unlike some of the other exoplanets mentioned, LHS 1140b has a higher chance of retaining a thick atmosphere due to its larger size and stronger gravity. If it has an atmosphere rich in greenhouse gases, it could maintain liquid water on its surface. Scientists are also investigating K218b, a planet located 124 light-years away, which made headlines when researchers detected water vapor in its atmosphere. Although K218b is classified as a mini-Neptune and may have a thick gaseous atmosphere, the presence of water vapor suggests that liquid water could exist on its surface or in the clouds. However, its thick atmosphere may also create high-pressure conditions that make life as we know it unlikely. Despite these exciting discoveries, confirming whether these planets are truly habitable remains a challenge. Current telescopes can only provide limited information about exoplanets, such as their size, orbit, and in some cases, atmospheric composition. Determining if a planet has a stable climate, liquid water, or even signs of life will require the next generation of space telescopes. The James Webb Space Telescope has already begun analyzing the atmospheres of exoplanets, searching for gases that could indicate biological activity. Future missions, such as the Habitable Worlds Observatory and the Extremely Large Telescope, will provide even more detailed observations, allowing scientists to study exoplanets with unprecedented precision. These telescopes will look for biosignatures, chemical signs of life such as oxygen, methane, and carbon dioxide, which could indicate that a planet hosts living organisms. Another exciting possibility is direct imaging, where future telescopes may be able to capture actual pictures of distant exoplanets. This would allow scientists to study surface features, weather patterns, and even the presence of oceans or continents. While this technology is still in its early stages, advances in adaptive optics and space-based observatories may one day allow us to see Earth-like planets in remarkable detail. As technology continues to improve, the dream of finding another Earth becomes more achievable. Each discovery brings us closer to answering one of the most profound questions in science. Are we alone in the universe? While no planet has yet been confirmed to host life, the sheer number of potentially habitable worlds suggests that life beyond Earth may be more common than we once thought. Many of these planets orbit stars different from our Sun, but could they still support life? Let's take a deeper look. Red dwarf stars are the most common type of star in the universe, making up nearly 70% of all stars in our galaxy. Because they are smaller, cooler, and much longer lived than Sun-like stars, they have become a major focus in the search for habitable exoplanets. In recent years, many of the most promising Earth-like planets have been discovered orbiting red dwarfs. This raises a critical question. Can planets around these small stars truly support life, or are they too extreme to be habitable? One of the main reasons red dwarfs are ideal for exoplanet searches is their relatively low brightness. This makes it easier for astronomers to detect planets using the transit method, where a planet passing in front of its star causes a noticeable dip in brightness. Because red dwarfs are much smaller than the Sun, even an Earth-sized planet can create a significant dip in light, making these planets easier to find compared to those around larger stars. This has led to the discovery of numerous potentially habitable exoplanets, including the famous TRAPPIST-1 system and Proxima Centauri b. One of the biggest advantages of planets orbiting red dwarfs is that these stars burn fuel at an incredibly slow rate, allowing them to shine for hundreds of billions or even trillions of years, far longer than the Sun's estimated lifespan of 10 billion years. This means that a habitable planet in orbit around a red dwarf could have an exceptionally long period to develop and sustain life. In theory, this could allow for the evolution of highly complex organisms, potentially even civilizations far older than humanity. However, there are significant challenges to habitability around red dwarfs. One of the biggest concerns is tidal locking, a phenomenon that occurs when a planet's rotation slows until one side permanently faces its star, while the other remains in perpetual darkness. This is common for planets orbiting close to red dwarfs because their weaker gravitational pull allows planets to settle into these locked orbits over time. A tidally locked planet would have one scorching hot side bathed in constant daylight and one freezing cold side trapped in eternal night. The extreme temperature differences between the two hemispheres could create violent winds and harsh climate conditions. However, if a planet has a thick enough atmosphere, winds could distribute heat from the day side to the night side, potentially allowing for a stable, habitable zone along the terminator line, the region where day and night meet. Some scientists believe that life could exist in this narrow strip of twilight, where temperatures remain relatively moderate. Another major concern is the intense stellar activity of red dwarfs. While these stars are small and dim, they can be extremely violent, frequently releasing powerful solar flares and bursts of radiation. Some red dwarfs, particularly young ones, can produce flares thousands of times more intense than those from the Sun. These flares can strip away a planet's atmosphere, exposing its surface to deadly radiation and making it nearly impossible for life to survive. Even planets that start with thick atmospheres could lose them over time if their star is highly active. Proxima Centauri b, the closest known exoplanet in the habitable zone, is a prime example of this challenge. Despite being an Earth-sized planet located at the right distance from its star to support liquid water, Proxima Centauri is known for its intense solar flares. These flares release powerful bursts of X-rays and ultraviolet radiation, which could gradually erode the planet's atmosphere. If Proxima Centauri b lacks a strong magnetic field, it may have lost much of its protective atmosphere, making it less likely to support life. The TRAPPIST-1 system, home to 7 Earth-sized planets, also faces this challenge. although 3 of its planets are in the habitable zone. TRAPPIST-1 is an active red dwarf that frequently emits flares. However, some scientists believe that if these planets formed with thick atmospheres or strong magnetic fields, they might have retained enough protection to sustain habitable conditions. Future observations with the James Webb Space Telescope and other advanced instruments will help determine whether these planets still have atmospheres, and if so, what they are made of. Despite these challenges, red dwarf planets remain a major focus of exoplanet research. One reason is their sheer abundance. Because red dwarfs are so common, the odds of finding a habitable planet around one are statistically much higher than around sun-like stars. Additionally, because red dwarfs burn for trillions of years, planets that manage to develop stable atmospheres could have long periods of habitability, potentially giving life plenty of time to evolve. Scientists are also exploring alternative ways that life could survive on red dwarf planets. One possibility is that organisms could evolve biological adaptations to survive extreme radiation, similar to how some bacteria on Earth thrive in high radiation environments. Another theory is that life could exist underground or in deep oceans, where it would be shielded from harmful stellar activity. If these planets have subsurface oceans, like Jupiter's moon Europa, life could be protected from radiation while still benefiting from the heat generated by the planet's core. While red dwarfs have become a major focus in the search for habitable planets, astronomers are also searching for planets around sun-like stars. These stars, known as G-type stars, are much less common than red dwarfs, but provide a more stable environment for life. Unlike red dwarfs, which can emit dangerous flares, G-type stars, like our Sun, have relatively mild solar activity, reducing the risk of atmosphere loss and radiation exposure. Additionally, planets around Sun-like stars are less likely to be tidally locked, which means they can have more Earth-like day-night cycles and climates. The search for planets around Sun-like stars is more challenging because these stars are larger and brighter, making it harder to detect small planets using the transit method. However, new telescopes and detection techniques are improving our ability to find Earth-like planets in these systems. NASA's upcoming Habitable Worlds Observatory and other next-generation missions will focus on directly imaging planets around Sun-like stars, allowing scientists to analyze their atmospheres and search for signs of life. The debate between the habitability of red dwarf planets and those around Sun-like stars remains open. While red dwarfs offer many potential targets due to their abundance, their violent stellar activity presents significant obstacles to life. Meanwhile, planets around Sun-like stars may provide a more stable environment, but they are harder to detect. Future discoveries will help determine which type of star system is more likely to host another Earth. While red dwarf planets are intriguing, the search for another Earth has many challenges. Let's explore what makes this search so difficult. Finding another Earth is one of the most difficult challenges in modern astronomy. While thousands of exoplanets have been discovered identifying a true Earth twin, a small rocky planet in the habitable zone with the right atmosphere and conditions for life remains elusive. The methods used to detect exoplanets have given us incredible insights, but they also come with significant limitations. From false positives to the difficulties of atmospheric analysis, the search for a second Earth is filled with obstacles. Yet, as technology advances, new methods and instruments are bringing us closer than ever to making this discovery. One of the main difficulties in finding another Earth lies in how exoplanets are detected. The most widely used method is the transit method, which involves monitoring the brightness of a star and looking for tiny dips in light when a planet passes in front of it. This technique has been responsible for the discovery of thousands of exoplanets, especially by telescopes like Kepler and TESS. However, this method favors large planets that create a more noticeable dip in brightness. A small Earth-sized planet causes only a tiny reduction in light, making it much harder to detect. Additionally, the transit method only works for planetary systems that are aligned in such a way that their planets cross directly in front of their stars from our perspective. Many Earth-like planets could remain undetected simply because their orbits do not allow them to be observed in this way. Another key detection method is the radial velocity method, which measures the gravitational tug that a planet exerts on its star. As a planet orbits, it causes its star to wobble slightly, shifting the wavelength of its light. This method has been successful in identifying many exoplanets, but it works best for massive planets that create a strong gravitational effect. Earth-sized planets have a much smaller impact, making them harder to detect using this technique. Additionally, the radial velocity method does not provide direct information about a planet's atmosphere or surface conditions, which are crucial for determining habitability. A more direct but extremely challenging approach is direct imaging, where telescopes attempt to capture actual pictures of exoplanets. This is incredibly difficult because planets are much dimmer than their stars, and the light from the star often drowns out the planet completely. Current direct imaging techniques work best for large gas giants that are far from their stars, but imaging small, rocky planets in the habitable zone remains beyond our current capabilities. Future telescopes equipped with advanced coronagraphs and starshades may allow us to block out starlight more effectively and directly observe Earth-like planets. Even when a planet is detected, determining whether it is truly Earth-like presents another major challenge. False positives can occur when something that appears to be a planet turns out to be something else, such as a background star or an instrumental error. Additionally, some planets that initially seem habitable based on their size and distance from their star may turn out to have conditions that make life impossible. For example, Venus is similar in size to Earth and orbits within the Sun's habitable zone, but its thick atmosphere creates an extreme greenhouse effect, making its surface incredibly hot and inhospitable. One of the biggest obstacles in confirming an exoplanet's habitability is analyzing its atmosphere. The presence of certain gases, such as oxygen and methane, could indicate biological activity, but detecting these gases from light years away is extremely difficult. Currently, astronomers use a technique called transmission spectroscopy, where they study the starlight that passes through a planet's atmosphere during a transit. By analyzing how different wavelengths of light are absorbed, scientists can determine the composition of the atmosphere. However, this method requires an exoplanet to transit its star from our viewpoint, which, as mentioned earlier, is rare. Additionally, clouds and haze can make it difficult to accurately interpret atmospheric data. Another problem is that some of the most promising planets are simply too far away for detailed study. Many Earth-like candidates discovered by Kepler are hundreds or even thousands of light years away. Even though we can detect their presence, we lack the technology to analyze their atmospheres or determine if they truly have conditions suitable for life. To find an Earth twin, we need to focus on exoplanets that are close enough for follow-up observations using powerful telescopes. Despite these challenges, new detection techniques are making it increasingly possible to find true Earth analogues. The James Webb Space Telescope is already revolutionizing exoplanet research by analyzing the atmospheres of distant worlds with greater precision than ever before. Upcoming missions like the Habitable Worlds Observatory and the Nancy Grace Roman Space Telescope will be even more powerful, allowing us to detect smaller planets and analyze their atmospheres in unprecedented detail. Scientists are also developing starshades, massive space-based screens designed to block out a star's light, making it easier to directly image planets orbiting close to it. These innovations could finally allow us to see an Earth-like planet as more than just a distant data point. One of the most exciting possibilities is the direct imaging of an Earth-like planet. If we could capture an actual picture of an exoplanet with oceans, continents, and an atmosphere rich in oxygen, it would be one of the most profound discoveries in history. Scientists are currently working on designs for telescopes capable of achieving this, such as the proposed LUVOIR, Large Ultraviolet Optical Infrared Surveyor, which could provide images of exoplanets with remarkable clarity. While this technology is still in development, it represents a major step toward identifying true Earth twins. The search for another Earth is a difficult and complex challenge, but it is not impossible. With each new discovery, we refine our understanding of what makes a planet habitable and develop better tools to find them. While it may take years or even decades to find a planet that truly mirrors Earth in every way, we are closer than ever before. While finding another Earth is difficult, some planets might actually be even better than our own. The idea of a super-habitable planet is one that challenges the traditional thinking behind exoplanet exploration. For decades, astronomers have focused on finding another Earth, a planet that closely mirrors our own in size, temperature, and atmospheric composition. But what if there are planets out there that are even more suitable for life than Earth? Some scientists believe that the conditions on Earth, while favorable, are not necessarily the best possible environment for sustaining life. Instead, a planet with a slightly larger size, a thicker atmosphere, and a more stable climate could potentially be even more habitable than our own world. One key factor that could make a planet super habitable is size. Earth is classified as a terrestrial planet, but it is on the smaller side compared to the wide variety of exoplanets we've discovered. A slightly larger planet, about 1.2 to 1.5 times Earth's radius, would have stronger surface gravity, which could help it hold onto a denser atmosphere. This, in turn, could provide more stable weather patterns and better protection from harmful cosmic radiation. A thicker atmosphere would also help regulate temperature more effectively, reducing extreme seasonal changes that could threaten life. Another factor that could contribute to superhabitability is oxygen levels. On Earth, the balance of oxygen in our atmosphere has played a crucial role in the evolution of complex life. Planets with slightly higher oxygen concentrations than Earth could encourage the development of larger, more energy-efficient organisms. A world with an oxygen-rich atmosphere could allow life forms to grow bigger and thrive in ways that may not be possible under Earth's conditions. However, there is a limit. Too much oxygen could make a planet more prone to wildfires, so the right balance is essential. Biodiversity and climate stability are also major considerations. Earth's biosphere is heavily influenced by plate tectonics, ocean currents, and a balance between greenhouse gases. A super-habitable world might have shallower oceans and more scattered land masses, creating diverse environments for life to evolve. Additionally, a planet with a slightly cooler star and a more stable orbit could avoid extreme climate shifts, providing a consistent environment where life could flourish for billions of years. Earth itself has undergone several mass extinction events due to climate fluctuations, asteroid impacts, and volcanic activity. A planet with fewer such disruptions might allow life to develop uninterrupted for longer periods. The role of gravity in shaping life is another intriguing factor. A world with slightly lower gravity could enable larger land-dwelling organisms, similar to how the reduced gravity on Mars allows for taller geological structures compared to Earth. On a lower gravity planet, animals and plants might evolve to be more massive, with towering forests and gigantic creatures capable of reaching sizes impossible on Earth. Conversely, if gravity were too low, an atmosphere could escape more easily, leading to a dry, barren world. Astronomers have already identified several candidates for super-habitable planets, worlds that could, at least in theory, be even better for life than Earth. One of the most promising is Kepler 142c, a planet that is about 1.4 times Earth's radius and orbits in the habitable zone of an orange dwarf star. Orange dwarfs, which are slightly cooler and longer lived than our Sun, provide a more stable environment for billions of years. Kepler 142c is thought to have a thick atmosphere and moderate temperatures, making it a strong candidate for habitability. Another intriguing candidate is K218b, a planet located about 124 light-years away. This world is a super-Earth, meaning it is larger than Earth but smaller than a gas giant. Recent studies suggest that it may have an atmosphere rich in hydrogen and water vapor, potentially indicating the presence of liquid water. However, some scientists question whether its dense atmosphere would create a runaway greenhouse effect, making it more like a mini Neptune than a true super-habitable planet. Then there is Teegarden b, a planet located just 12 light-years away in the habitable zone of its star. While we don't yet have enough data to confirm whether it is truly super-habitable, it remains a fascinating candidate for further study. The discovery of these potentially super-habitable worlds raises a fundamental question. If given the choice, should humanity seek out another Earth, or should we aim for something even better? While Earth is the only home we have ever known, there is no rule that says it is the best possible place for life. If planets with superior conditions exist, they might offer us a glimpse of what an ideal world could look like. However, superhabitable planets may not be as common as traditional Earth-like worlds. Finding them requires refining our search methods and expanding our criteria for habitability. Future space telescopes, such as the Habitable Worlds Observatory and next-generation exoplanet survey missions, will help us determine which planets have the right mix of atmosphere, temperature, and stability to support life for billions of years. While searching for planets, we often focus on worlds that resemble Earth, but what about habitable moons? For centuries, astronomers have focused on planets as the most likely candidates for hosting life. However, recent discoveries suggest that moons, even those far from their star's habitable zone, could be the true cradles of life. In our own solar system, moons like Europa and Enceladus hold vast subsurface oceans beneath thick ice crusts, warmed not by sunlight, but by the gravitational pull of their host planets. If similar exomoons exist around giant planets in other star systems, they could provide some of the most promising environments for alien life. One of the most exciting possibilities for habitable moons is their ability to exist outside traditional habitable zones. Planets need to orbit within a specific distance from their star, the so-called Goldilocks zone, for liquid water to exist. However, moons can maintain warm conditions even if their host planets are in freezing regions of space. This is due to tidal heating, a process in which the immense gravitational forces of a massive planet stretch and squeeze the moon's interior, generating heat through friction. This process allows moons like Europa, which orbits Jupiter well beyond the Sun's habitable zone, to maintain liquid water beneath its icy surface. If similar tidal heating occurs in exomoons around distant gas giants, they could sustain subsurface oceans for billions of years, potentially providing an environment for life to thrive. In our own solar system, Europa and Enceladus are two of the best examples of how moons could sustain life. Europa, one of Jupiter's largest moons, is covered by an ice shell that is estimated to be 10 to 30 kilometers thick, beneath which lies an ocean containing more water than all of Earth's oceans combined. Scientists believe this ocean is in direct contact with the moon's rocky mantle, allowing for potential hydrothermal vents that could provide nutrients and energy, just like the deep-sea vents on Earth that support life without sunlight. Saturn's moon, Enceladus, is equally intriguing. It has geysers that shoot plumes of water vapor and organic molecules into space, hinting at an underground ocean rich in the ingredients necessary for life. These plumes contain complex organic compounds, leading some researchers to speculate that Enceladus could harbor microbial life beneath its frozen surface. If moons in our solar system can sustain liquid water despite their frigid locations, then exomoons orbiting distant exoplanets might also be prime locations for habitability. One of the biggest challenges in searching for habitable exomoons is that they are much harder to detect than exoplanets. While the transit method, which measures dips in starlight when a planet passes in front of its star, is excellent for detecting large planets, it is less effective for moons. Because moons are smaller and orbit close to their host planets, their signals are often overshadowed. However, astronomers have developed techniques to spot exomoons by looking for tiny variations in a planet's transit timing caused by the gravitational pull of an orbiting moon. One of the first strong candidates for an exomoon is Kepler 1625b, an enormous moon orbiting a gas giant about 8,000 light-years away. This potential exomoon is estimated to be several times larger than Earth, making it more of a mini Neptune than a rocky moon. But its discovery proves that moons can exist around exoplanets and might be common in the universe. If more Earth-sized exomoons are discovered, they could open up entirely new possibilities for life. One advantage that moons may have over planets is a more dynamic environment for habitability. Many exomoons would experience constant tidal forces, which could drive geological activity, generate heat, and support long-term liquid water stability. Additionally, moons in tight orbits around large planets would be protected from cosmic threats like asteroid impacts, since their host planet could act as a shield, much like Jupiter does for some of its moons. Moons could also experience double energy sources, not just from the light of their star, but also from the reflected light and radiation of their host planet. This means that a habitable exomoon might remain warm even if its star is faint or distant. If such a moon has an atmosphere capable of trapping heat, it could remain stable for billions of years, allowing life plenty of time to develop and evolve. However, habitable moons would also face unique challenges. If they are too close to their gas giant host, they may be bombarded with intense radiation and magnetic fields, similar to how Jupiter's powerful radiation belt makes some of its moons highly inhospitable. Additionally, a moon's atmosphere could be stripped away if it is not large enough to maintain a strong gravitational hold. Despite these difficulties, the sheer number of gas giants discovered in exoplanet systems suggests that habitable exomoons could be widespread, even if we have yet to confirm one beyond our solar system. The search for exomoons is still in its infancy, but advancements in telescope technology will soon provide more definitive answers. The James Webb Space Telescope and future observatories, like the Habitable Worlds Observatory, will be able to analyze distant star systems with much greater precision. Some astronomers predict that the discovery of the first confirmed habitable exomoon is only a matter of time. If exomoons are as common as planets, they could vastly expand the number of places where life might exist. If habitable exomoons exist, they might challenge the long-held belief that planets are the only viable places for life. In fact, they could even outnumber habitable planets, offering even more potential homes for life beyond Earth. As our technology advances, the search for another Earth is rapidly changing. Let's explore the cutting-edge tools leading this search. The search for another Earth has come a long way, but the real breakthroughs are yet to come. As technology advances, we are moving closer to answering one of humanity's greatest questions. Are we alone in the universe? With next-generation telescopes, artificial intelligence, and revolutionary space missions, we are on the brink of a new era in exoplanet research. These tools will not only help us find Earth-like planets with greater precision, but might also provide the first direct evidence of alien life. One of the most important advances in the search for habitable exoplanets is the development of next-generation space telescopes. The James Webb Space Telescope, JWST, has already begun transforming our understanding of exoplanet atmospheres by analyzing the light that passes through them. However, JWST is just the beginning. Future missions like the Habitable Worlds Observatory and the Extremely Large Telescope, ELT, will take this research even further. These observatories will have the power to directly image small, rocky planets and study their atmospheres in unprecedented detail. One of the biggest challenges in detecting exoplanets is that they are incredibly dim compared to their host stars. A planet like Earth, for example, reflects only a tiny fraction of the light that its star emits. To solve this problem, astronomers are developing starshade missions, a revolutionary technique that will allow us to block out starlight and reveal the faint glow of orbiting planets. A starshade is essentially a giant space-based disk positioned between a telescope and a distant star, allowing the telescope to see planets that would otherwise be lost in the glare. If successful, this technology could enable us to take detailed images of Earth-like planets and even detect signs of life in their atmospheres. Another groundbreaking technology in exoplanet research is spectroscopy. When light from a star passes through a planet's atmosphere, it gets filtered in specific ways depending on the gases present. By studying the light spectrum of an exoplanet, scientists can determine whether its atmosphere contains key ingredients for life, such as oxygen, methane, and water vapor. This method has already been used to detect elements in the atmospheres of hot Jupiters, But future telescopes will allow us to analyze the atmospheres of smaller, potentially habitable planets. If we ever detect a strong combination of biosignature gases, it could be the first evidence of alien life. Artificial intelligence, AI, and machine learning are also playing a major role in exoplanet detection. The vast amount of data collected by telescopes like Kepler, TESS, and JWST is far too large for human astronomers to analyze manually. AI-powered algorithms can quickly sift through this data, identifying subtle patterns and detecting exoplanets that might otherwise be missed. In 2018, researchers using AI discovered 2 new exoplanets in Kepler's data that had gone unnoticed for years. As AI models become more advanced, they will help us discover even smaller, Earth-like worlds in distant star systems. One of the most exciting frontiers in exoplanet research is quantum computing. Traditional computers struggle with the enormous complexity of modeling planetary atmospheres and processing the vast datasets from space telescopes. However, quantum computers, machines that harness the strange properties of quantum mechanics, could perform calculations millions of times faster than conventional supercomputers. This could enable scientists to simulate entire planetary environments with extreme accuracy, allowing us to predict which exoplanets are most likely to be habitable. But will we ever be able to detect life directly? This is the ultimate goal of exoplanet research. Right now, our best bet is to look for biosignatures, chemical markers that suggest biological activity. For example, on Earth, plants and bacteria produce oxygen as a byproduct of photosynthesis. If we were to find a planet with high levels of oxygen alongside methane, it would be a strong indicator that life exists there. However, biosignatures alone are not enough. Some chemical processes, such as volcanic activity, can mimic biological signals. To confirm the presence of life, we will need to observe planetary surfaces, detect seasonal changes, or even see direct evidence of alien ecosystems. Future missions might send robotic probes to analyze exoplanet atmospheres in more detail, or use powerful space-based telescopes to capture images of distant worlds. The Breakthrough Starshot initiative is one of the most ambitious projects aiming to take this search beyond telescopes. It proposes sending a fleet of tiny laser-powered spacecraft to the Alpha Centauri system, home to Proxima Centauri b, the closest known Earth-like exoplanet. These spacecraft, known as starships, could travel at up to 20% the speed of light, reaching Alpha Centauri in just 20 years. If successful, they could capture the first close-up images of an exoplanet and potentially detect signs of habitability or even life. The future of exoplanet exploration is bright. With cutting-edge technology, artificial intelligence, and the possibility of interstellar missions, we are closer than ever to discovering another Earth. But even if we find a world that mirrors our own, one question remains: could we ever travel there? The dream of visiting an Earth-like exoplanet has long been a staple of science fiction, but in reality, the challenges of interstellar travel are immense. The sheer vastness of space makes the journey to another Earth an almost insurmountable task with current technology. Even the closest known potentially habitable exoplanet, Proxima Centauri b, is over 4 light-years away, which translates to 40 trillion kilometers. With today's fastest spacecraft, it would take over 70,000 years to reach this distant world. Clearly, if we ever want to explore exoplanets firsthand, we will need revolutionary advances in space travel. One of the biggest obstacles is propulsion. Current rocket technology, which relies on chemical fuels, is far too slow for interstellar travel. To reach another Earth-like planet within a human lifetime, we would need to develop advanced propulsion systems capable of traveling at a significant fraction of the speed of light. Scientists have proposed several theoretical methods that could make this possible. One such idea is the warp drive, a concept that comes straight from science fiction but is based on real physics. Proposed by physicist Miguel Alcubierre, a warp drive would create a bubble in space-time, allowing a spacecraft to surf faster than light without violating the laws of physics. However, the energy requirements for such a drive are beyond anything we can currently produce. Some estimates suggest we would need the energy equivalent of an entire star to make it work. A more feasible option might be antimatter propulsion. Antimatter is the most energy-dense substance known, capable of releasing nearly 100% of its mass as energy when it interacts with normal matter. If we could develop a way to produce and store antimatter in large quantities, we could build spacecraft that travel at speeds close to 10% the speed of light. Even at that speed, reaching Proxima Centauri b would take over 40 years, but it is a significant improvement over current technology. The challenge is that antimatter is extremely difficult to produce and even harder to contain. Another promising idea is laser sail propulsion, the technology behind the breakthrough Starshot initiative. This concept involves a tiny, lightweight spacecraft attached to an ultra-thin sail, which is then accelerated by high-powered lasers from Earth. In theory, these spacecraft could reach speeds of up to 20% the speed of light, allowing them to reach Proxima Centauri in 20 years. However, these probes would be small and unable to carry human passengers, limiting their use to robotic exploration. Even if we found a way to send humans to another Earth-like planet, the journey itself would pose enormous challenges. One potential solution is the concept of generation ships, massive self-sustaining spacecraft where multiple generations of humans would be born, live, and die before their descendants finally reach their destination. While this might seem like a practical approach, it raises difficult questions. How would society function in an enclosed environment for centuries? Could people remain motivated for a mission they would never live to see completed? And what if, after hundreds of years, the destination turned out to be uninhabitable? For those who dream of colonizing a new world, there would be further challenges once we arrived. Terraforming, modifying a planet's environment to make it more Earth-like, would take centuries, if not millennia. We would need to ensure the planet had a breathable atmosphere, suitable temperatures, and liquid water. If the planet's gravity was too strong or too weak, it could have major effects on human physiology. And then there is the issue of space radiation. Without a protective magnetic field, humans on an alien world would be exposed to dangerous levels of cosmic radiation, which could cause long-term health problems. But perhaps the greatest dilemma in colonizing an exoplanet is the ethical question: what if the planet already has life? Throughout history, human exploration has often led to the destruction of indigenous ecosystems. If we found microbial life on an exoplanet, would we have the right to colonize it? What if that life was more complex, perhaps even intelligent? Would we attempt to coexist? Or would history repeat itself with conquest and exploitation? These are questions we must carefully consider before making any attempt to settle another world. If traveling to an exoplanet is too difficult, could we instead send robotic explorers? This is a more practical option in the near future. The Breakthrough Starshot initiative aims to send tiny spacecraft to nearby star systems, taking pictures and sending back data. Future missions could send larger probes equipped with AI, capable of analyzing planets in detail. Perhaps one day, these robotic explorers could even land on an alien world and study it as our rovers do on Mars. Despite all these challenges, the dream of visiting another Earth remains one of the most exciting possibilities in science. Whether through human travel or robotic missions, the desire to explore beyond our solar system is deeply embedded in our nature. But beyond the technological hurdles, one question remains. How would the discovery of another Earth change humanity itself? The discovery of another Earth would be one of the most profound moments in human history. It would reshape our understanding of the universe and force us to reconsider our place in the cosmic order. For centuries, we have looked up at the stars and wondered whether other worlds like ours exist. Now, as science brings us closer to answering this question, we must also prepare for the implications of what such a discovery would mean for our civilization. One of the biggest questions that finding another Earth would answer is whether life is common in the universe. If we discover a planet that is nearly identical to our own, one with liquid water, a stable atmosphere, and conditions suitable for life, it would strongly suggest that Earth is not unique. The sheer number of exoplanets already found implies that there are likely billions of potentially habitable worlds in the galaxy. If just one of them harbors life, then the chances are high that life exists in many places. It would mean that the universe is not an empty void, but a thriving ecosystem of worlds, each with the potential to support biology in some form. The implications of such a discovery would go beyond science. It would deeply impact philosophy, religion, and human culture. Throughout history, many belief systems have placed Earth at the center of creation. If we find another Earth, especially one teeming with life, how would that affect religious perspectives? Would it challenge traditional ideas about humanity's uniqueness? Or would it reinforce the notion that life is a fundamental part of the universe's design? Different cultures and belief systems would likely interpret the discovery in various ways, sparking new discussions about the meaning of life and our role in the cosmos. From a scientific standpoint, discovering another Earth would open up an entirely new field of research. If we detect signs of life, whether through atmospheric biosignatures, chemical imbalances that suggest biological processes, or even direct images of alien organisms, it would be the most groundbreaking moment in biology. If this life is similar to Earth's, it might suggest a shared cosmic origin, supporting the theory of panspermia, which proposes that life spreads between planets through meteors and comets. But if extraterrestrial life is completely different, using a chemistry unfamiliar to us, it would prove that life is not just an Earth phenomenon, but something that can arise in diverse ways throughout the universe. Beyond the scientific and philosophical implications, the discovery of another Earth would also have political and economic consequences. Governments and space agencies around the world would likely react in different ways. Some nations might see it as an opportunity to push for increased space exploration funding, while others might view it as a distant curiosity with little immediate impact. Spacefaring nations like the United States, China, and private companies such as SpaceX could intensify their efforts to develop interstellar travel technologies, hoping to be the first to explore or even claim a new world. This raises the question of whether such a discovery would unite or divide humanity. Historically, major scientific discoveries have often sparked competition, as seen in the space race of the 20th century. If another Earth-like planet is found, will countries work together to study and explore it, or will they race to stake a claim? Could this discovery bring about new international cooperation, leading to a united effort to reach the stars? Or would it deepen geopolitical tensions, with nations fighting over who gets to explore first? If the newly discovered planet hosts intelligent life, the implications become even more complex. The idea of interstellar diplomacy is often explored in science fiction, but what would it look like in reality? If another civilization exists, how would we communicate with them? Would they be peaceful, or would they see us as a potential threat? Would we even be able to understand their way of thinking? The challenges of communicating across interstellar distances are immense, but the very existence of another intelligent species would change the way we view ourselves. It could answer the question of whether intelligence is a rare evolutionary trait or something that arises frequently in the universe. Another profound question that would arise is whether humans would ever leave Earth for another planet. If we discover a true Earth twin, one that is not only habitable, but possibly even more suitable for life than our own, would people want to migrate? The idea of a second home for humanity is appealing, especially in the face of climate change, overpopulation, and resource depletion. A new Earth could represent a fresh start, a world where humans could build a society from scratch. However, the journey to such a planet would be an immense challenge. The nearest Earth-like exoplanets are light years away, requiring centuries or even millennia of travel with current technology. Even if interstellar travel became possible, who would be chosen to go? Would it be a select few, scientists, engineers, and leaders, tasked with representing humanity? Or would it be an open migration, allowing anyone willing to start a new life on an alien world? The social and ethical implications of colonizing another planet would be enormous. What kind of government would be established? What laws and rules would govern this new society? Would we treat this new Earth with the same care that we failed to show our own planet? Or would we repeat the same mistakes? But there is also another perspective. Should we even leave Earth at all? Some argue that rather than seeking a new home elsewhere, we should focus on preserving and repairing the planet we already have. Earth is uniquely suited to life because it is the only home we have ever known. No matter how similar another planet may be, it will never be exactly like Earth. It may have different gravity, a different atmosphere, or unknown environmental dangers. If we cannot take care of our own planet, would we be any better at taking care of a new one? In the end, the search for another Earth is not just about finding a new place to live. It is about understanding who we are. Every exoplanet we discover, every distant world we study, brings us closer to answering the ultimate question: are we alone? Whether or not we find an exact twin of our planet, each new discovery expands our knowledge of the universe and reminds us that we are part of something much greater than ourselves. The moment we find another Earth, whether it is a lifeless but habitable world, a thriving alien ecosystem, or even a planet harboring intelligent beings, will be a turning point for humanity. It will force us to look beyond our divisions, beyond our conflicts, and recognize that we are all passengers on a tiny blue world floating through the vastness of space. And when that day comes, will we see it as a challenge to reach for the stars, or as a reminder that our own world, fragile yet full of life, is worth protecting?